Okay. Good afternoon, everyone. So, in the last lecture, if you recall, we have completed Unit 5. Unit 5 has been completed. So, Unit 4 and Unit 5, these two units are part of your syllabus in mid-sem. Okay? So, now what I want to start is Unit 6. Unit 6 is the last unit of graph theory. So, in this unit, we will learn about what is a planar and non-planar, or planarity or non-planarity of graph. So let's start without wasting time. So unit number 6, we are going to start today. Planar and non-planar graph. Unit number 6, a planar and non-planar graph. Okay, so let's proceed with the content. What actually we are going to learn throughout this chapter. Planar and non-planar graph. Then we will go for graph embedding. At next, we'll go for Kuratowski's first and second theorem, which is a very important theorem, Kuratowski's theorem. Later on, we'll go for Euler's formula and dual of a graph. At last, we'll end up with graph coloring and region coloring. These two important concepts. So this is what actually included in your syllabus of graph theory. After that, we'll move on to discrete mathematics. Unit 1, Unit 2, Unit 3. Let's proceed for Unit 6. The very first thing is, what is a planar graph? Now, a graph G said to be planar if it can be drawn on a plane so that no two edges cross each other at a non-vertex point. Otherwise, it is called a non-planar graph. In a simple language, what is a planar graph? First of all, the basic definition of planar graph: if edge cross is there, if two edges cross each other, then that graph is not a planar graph. It's a non-planar graph. For any graph, if there exists no edge which cross each other, that graph is known as a planar graph. So first graph, if you observe, each and every edges are not having any crossing. The first graph is having no crossing or no crossover. Okay, all the edges are very smooth. So this graph is an example of planar graph. Similarly, the second graph, if you observe, it is a non-planar graph because there is an edge crossover. If you observe this edge, all three edges are having a crossover at this point. This is a non-vertex point. This is not a vertex. So there is a non-vertex point where the edge is having a crossover. So edge crossover at non-vertex point implies it's going to be a non-planar graph. Okay? Now, note it down, all of you. Brother, if it was a vertex, then it is also planar. Yes, if it was a vertex, suppose this is a vertex. Then there is no crossover. Burhanuddin, if suppose this is a vertex, then there is no crossover. So this is a planar graph. Then it is going to be a planar graph. But in this case, it is not a vertex. That's why it's a non-planar graph. Okay. One vertex can be planar. Yes, one vertex is a example of planar graph. Okay. Right. Proceed. Now, what is this embedding? What is an embedding? A drawing of geometric representation of a graph on any surface. Drawing of geometric representation of a graph on any surface such that no edge intersects is called a embedding. A geometric graph G is a planar if there exists a graph isomorphic to G and that is embedded in a plane. Otherwise, it is non-planar. Now, what we will do, I will refine the definition of planar graph. So it's called refinement. I will refine the definition of planar graph. In the last slide, I told you a planar graph means there is no edge crossover. Now what I'm saying, it may be possible there is an edge crossover. It may be possible there is an edge crossover. But if I can redraw the graph, okay, edge crossover is there. Edge crossover is there. What I will do, I will redraw the graph and there will be no edge crossover. That is in our hand. Redraw means what? We'll find isomorphism. So we will find an isomorphism, if it is possible, that we'll find an isomorphism which is having no edge crossover. No edge crossover means this is called embedding, graph embedding. So whenever you can successfully redraw a graph on a plane, without any edge crossover, that graph is known as graph embedding. Okay, if we cannot redraw, just a minute, a bit cold. All right. So now I'll give you an example. Let's consider this graph. Okay. These are the few graphs you can consider. Let's consider this graph. Now, this graph is apparently look like a non-planar graph, isn't it? Apparently, it look like a non-planar graph because it's a crossover. You tell me, sir, this is a crossover. This is a non-planar graph. But yes, you are right. It is a non-planar graph. There's no problem. But this non-planar graph is having a graph embedding. This non-planar graph, we can convert this graph into a planar graph, isn't it? Just by shifting this edge from outside. Shifting this edge from outside. Now this graph becomes a planar graph. This graph becomes a planar graph. There is no edge crossover. This process is known as graph embedding. So what is the graph embedding? Embedded graph. If someone asks you what is the embedded graph of this non-planar graph, this is going to be the embedded graph. Embedded graph. Which one is the embedded graph? This graph is known as embedded graph. Whenever embedded graph is possible, that means that graph becomes a planar graph. That graph become a planar graph. Now you may ask me, sir, what about this graph? Is this graph non-planar or planar? This graph now, after explaining this, now this graph becomes planar graph. Apparently look like non-planar, but it becomes planar graph because graph embedding is possible. Because graph embedding is possible. We can redraw the graph and we can make it planar. This is what actually mean by planar and non-planar graph. Tell me, clear or not?
Sir.
Yes.
Sir, suppose if you want to change it like to planar graph, like make it embedded graph, shape.
See, planar graph is always embedded. Yeah, shape, structure, it's possible, but still planar graph is always an embedded graph, like this graph. This graph is a planar graph. This graph is a planar graph. Right? This graph is a planar graph. Now this graph is also embedded graph because already is embedded means there is no edge crossover in a plane. This graph is already embedded graph. So there is no questions asked. Getting my point? So planar graph in 2D, in two-dimensional plane, planar graph in 2D are always embedded graph. There will no question asked. Only problem in case of non-planar graph. So whenever the non-planar graph is given to you, first you have to check. Don't say initially this is a non-planar. Edge crossover means non-planar. No. You have to check whether graph embedding is possible or not. If graph embedding possible, it's going to be, then it is planar graph. If graph embedding not possible, then it is a non-planar graph.
Sir, so can we say that every non-planar graph is a planar graph by the help of embedded graph?
Sorry?
Like suppose, sir, so then we can say that non-planar graphs, like every non-planar graph is called planar graph because the same vertices we can change it to embedded.
Every non-planar graph, how is every non-planar graph is a planar graph? Not every non-planar graph, we cannot make a embedded graph. Okay, like the last graph. This graph is a non-planar graph. You cannot make an embedded graph. You cannot find. Embedding is not possible for this graph. You can try. Embedding is not possible. Embedding is not possible for this graph. Okay, you can try. You can try hard. Understand? So this graph is a non-planar graph. You cannot say this is a planar graph. Okay? Yes, if embedding exists, then it's going to be a planar graph. That non-planar becomes a planar. All right. Any doubts till now? Otherwise, write C on chat box. If you have no doubts, then write C on chat box. Otherwise, ask your doubts. All right. Now proceed for some application. Application of planar graph. Just a minute. So application of some planar graph. Sometimes it is really important to have able to draw graph without edge crossings. Like if I talk about connecting some utilities. Utilities means, let's say electric wire and water wire and water pipe, electric pipe, natural gas pipe. 3 pipes are there. We want to connect them in such manner there is no edge crossover. If there is an edge crossover, then water, natural gas and electricity both will crash, and that is going to be a chaos. You don't want any edge crossover with the pipes, right? You want in such a manner they will attain that there will be no edge crossover. So this kind of scenario is there where we want a planar graph. Apparently, it looked like a non-planar graph. Whenever you draw the graph of these things, it look like a non-planar graph. But there should be a geometric embedding possible. Without geometric embedding, you cannot say this is going to be a planar graph. Okay, so always you need to construct that graph in such a manner there would be a geometric embedding. Okay. Now we'll go for two important graphs. It's known as Kuratowski's graphs or Kuratowski's two graphs. One is known as K5. K5 is a complete graph with 5 vertices. Another one is known as K33. K33 is a complete bipartite graph with 6 vertices. These two graphs are known as Kuratowski's graph. This is the first graph, Kuratowski's first graph, and this is the second graph, Kuratowski's second graph. I will tell you what's the importance of these two graphs. All right, now we'll have to prove this theorem. First, we have to prove the first thing, that a complete graph with 5 vertices is non-planar. Complete graph with 5 vertices is non-planar means K5 is non-planar. K5 means Kuratowski's first graph. You have to prove that. It's very important theorem. We can ask you, and this theorem is known as Kuratowski's first theorem. Kuratowski's first theorem. Kuratowski's first theorem, that theorem is known as like a complete graph with 5 vertex or vertices is always a non-planar. Let's go for the proof. First of all, without loss of generality, I want to prove that this graph is a non-planar graph. Non-planar means I want to prove that this graph is a non-planar graph. So first of all, you have to think that this graph is a planar graph, and we will try hard. We will try hard to show this graph. We can draw the geometric embedding. We can draw the geometric embedding of K5. This is what I will try. What is K5? What is K5? This graph is K5, isn't it? This graph is K5. So we will try to draw this graph without, we try to draw this graph, draw the geometric embedding of this graph. Draw a geometric embedding of this graph. Geometric embedding of this graph. We'll try. We will try. So for that reason, what I will start from? I will start from the border line. So what is the border line of this graph? This is the border line or outer line. These are the border line of the graph. This is by default a simple without edge crossing graph. This is a planar graph. This graph is a straightforward planar graph. No problem. But still, what we try to connect, we'll try to connect all the edges, inside edges. All the inside edges are remain here. We'll try to connect them in such a manner there will be no geometric embedding. I mean, there will be no edge crossover. There will be no edge crossover. Just a minute. Okay. So this graph is a planar graph. Now what we will do, we will try to connect the inside vertex. Let me give you the name of the vertex. First, this is V1, this is V1, V2, V3, V4, and V5. So first, what is written here? A complete graph, as you may recall, this simple graph in which every vertex is joined to every other vertex by means of an edge. This being the case, we must have a circuit. So this graph is a circuit. So what you have to draw every time? The outer circuit, the outermost circuit. So now this graph is a circuit. We must have a circuit going from V1 to V2, V2 to V3, V2 to V4, V2 to V5, V5 to V5, V5 to V1. And that is a pentagon. Obviously, this graph is a pentagon. Now this pentagon must divide the plane of the paper into two regions. Obviously, there will be two regions. Region means nothing but, I will tell you later in region what is the region exactly. But this time I just tell you that region means this is an inside region R1 and this is an outside region. Since the graph is a bounded one and it's a pentagon, region means a sector. Region means a sector, or you may say the number of partitions. Region means the partitions. So inside one is the one partition. Similarly, outer one is going to be another partitions. Outer means is always there will be an outer region. Inside region is there, inner region is always there. Apart from inner region, there will be another outer region always be there. Okay. Now, what's the next step? Now next step, gradually we will draw one by one lines, inside edges. Now in this case, since V1 and V1 is to be connected with V3, okay, by means of an edge, that edge may be drawn inside or outside the pentagon without intersecting 5 edges drawing previously. That is our target. That is what our target is. Okay, we will try to join all the edges without any intersections. Okay, without any edge crossovers. Now, in this case, we draw a line from V1 to V3. We'll draw a line from V1 to V3. This is a new line. Still, if you observe, we increase the regions, but there will be no edge crossover. Is there any edge crossover now? No edge crossover. Still, we are in a position to say this is a planar graph. Still, we are in a position to say this is a planar graph. Now we will try to join. Now look at this. Now we have to draw the edge from V2 to V4 and V2 to V5. Now, if I join these two things, V2 to V4 and V2 to V5, that will create problem. There will be an edge crossover. So we cannot join V2 to V5 and V2 to V4 from inside. From inside. That means from region R1. Inside means from region R1, outside means from region R2. So from inside we cannot join, but there is another possibility. From outside I can join. From outside I can join like this without edge crossover, right? Similarly, we can join this without edge crossover, right or wrong? So that is your next step. Look at this. We'll join them without edge crossover from outside. We'll join them without edge crossover from outside. Now, everything is near about done. Now, what are the lines remaining to join? What the lines are remaining to join? V3, V5 and V2, V4. So we will try to join V3, V5 and V2, V4 from without edge crossover. Let's try it. If not possible, then we'll fail. Understand? All right. So the next target is to join V2 and V4 and V3 and V5. All of you written these things? Writing completed? Done? Okay, so now let's proceed with the connection. Now what we will do next step, we'll connect V3 and V5. We'll connect V3 and V5. Only one edge is left. Now you tell me, I want to connect V2 and V4. Only one connection is left, V2 and V4. Is it possible to connect V2 and V4 without any crossover? From inside, outside, wherever. Is it possible? So crossover must be there. Crossover must be there. Right? Since the crossover must be there, so we will draw like this. This indicates a crossover. This indicates a crossover. Okay, so there is a crossover. So draw like this. This indicates a crossover. So since there is a crossover, so obviously this complete graph with 5 vertices is a planar graph or non-planar graph? Planar graph or non-planar graph? Non-planar graph, right? Getting my point? That is how we will prove this thing. So simple stuff, we'll prove it in a complicated manner, right? Any doubts, please ask me. Yes. Right? So you can try infinite possibilities, all other possibilities. If you want to join V2 and V3 like this manner, okay, sorry, V3 and V4, V3 and V5 like this manner, whatever is possible you can try, and at that time you have to prove that it is non-planar. It is planar, but you cannot find it is a planar graph. You cannot find any geometric embedding. That is why it's not possible. Okay. So Sunny Mohammed is writing like embedded exist, can be more than one edge or must be one edge. Embedded means, I didn't get your question, Mohammed Sunny Mohammed. Didn't get your question. Okay, all of you. So that is about the task today. So all of you think about this. Also, I will give you another graph. and think whether this graph is planar or non-planar. This is not any other, this is a simple graph. This is a simple graph. So try to think about that this graph is a planar graph or non-planar graph. Not a simple graph. I mean, this is a standard graph. I mean, okay, there is no name of this graph. Like last graph was Kuratowski's first graph, but it's a straightforward graph I give you. You have to think this is a planar or non-planar graph. Okay, Prince told me that is a planar graph. Okay, think about it. If there any geometric embedding is possible or not. Geometric embedding possible? Okay, Prince. Sorry, planar. Yeah, how? How it's a planar? So the problem is inside these two diagonals. So one diagonal we will delete. We'll delete one diagonal from inside and we will join that diagonal from outside. Right or wrong? Everything done? This graph become planar? Is an embedding? Is an embedding? Good. Well done, Prince. So this graph is a planar graph. Similarly, lots of graphs are there. Like if I ask you, what about Peterson graph? Think and tell me, Peterson graph is planar or non-planar? All of you think and tell me. Peterson graph is planar or non-planar? By that time, I will take you attendance. Okay, Asaf Noor, no problem. Are your screen is visible? Just a minute. Okay. So
So
TC4 roll number 23 to 36. TC4 roll number 23 to 36. Okay, 37 to 42. 37 to 42. 43 to 48.
46.
49 to 106. 49 to 106. 110 to 159. 110 to 159. 160 to 183. 160 to 183.
Sir, you didn't mark me present, sir.
2059.
TD1.
Hello.
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 126. TD1 126. 7 to 12. 7 to 12. 7 to 12. 7 to 12. 13 to 20. 13 to 20. 13 to 20. 13 to 20. Anyone else? TD1. Anyone else?
Hello. Hello, sir.
Okay, TC4. Anyone else?
Yes, sir.
Hello, sir.
182.
182.
59.
120.
75.
Sir.
Okay, guys. Have a nice day.
75. 75.
Think about Peterson graph. We'll
One-
discuss on next stage.
Hello,
Have
sir.
a nice day. Bye.